So what we are doing there is your model performance of the model is measured using log likelihood. Log likelihood is a good metric that is provided. So in the tutorial, if you when you are running the model, you are presenting the log likelihood for the final is what is showing in R as the log likelihood. It also shows you the different metrics we showed in the here. It is showing the measure 1 and measure 2. It is showing rho square with respect to equal share model and rho square with respect to the market share model or the constant model. So usually we would like to present measure more reliable, and that is what is more relevant for this. On top of this, now the hypothesis testing that we did for linear regression that we talked about all these was same it applies to biological models also. We have a standard error. You just take the ratio of the coefficient and the standard error, and then that gives you the distance. If that is more than the 90% value or 95% value that you choose as a parameter, you can say that the variable is significant or not. Yeah, that's the process. So, but now what we need is how do we compare two different models? So if you have comparison that we need to do two different models, we can use what's called a log likelihood ratio. The LR test is the common test that we use. So if you have two models and one of them is nested with the other, okay, what I mean by that is say we're doing a binary logic model. So you have we try rebalancing. We try things. This is time. Estimating the coefficient. One is the constant, then we are estimating the common coefficient for travel. Okay, so there are two ways of estimating the effect of travel time coefficient. You can estimate a coefficient specific to the mode. So I could theoretically add T underscore drive, T underscore transit. This is what was available in the code that you saw yesterday, where we had a beta for air travel time and a beta for rail travel time separately. Okay, it's not necessary to do it separately. Again, there are different reasons why we'll do that. I'll talk about that. But let's say we have this one. In this, I'm saying the effect of travel time remains the same across all modes. Okay, same thing for cost. The effect of cost remains. There's only one beat, so I'm only estimating three parameters in this. If I treat these two as different, I get one extra here, I get one extra here, and 5 parameters in my model. Okay. So now, if I run this model, I have 3 parameters, I'll get a log likelihood. So let me call that one. Now, in this specification, I could add a new variable. We call it beta comfort in right, comfort in right. So model 1 has 3 variables. Model 2, but again I'm using comfort as the same variable for both of them. I only have one more extra coefficient. Model 2 will have 4 parameters. So if you get a participant. So which will have a better log likelihood? The model without comfort or the model with comfort? model with comfort should have an improved log because you're giving extra information to the model. Okay? So, how do I get model 1 from model 2? If I want to impose a constraint on model 2, what is the constraint I am imposing to convert model to model? If I say beta c is equal to, if beta c is equal to 0, model 2 collapses to model 1. Okay. So what we are showing here is model 1 is a restricted version of model 2. If I put a condition on model 2 that beta c has to be 0, it gives me model. So you can say model 2 is the unrestricted version of model 1. Does everybody see that? Okay, so if I can clearly see some conditions I can impose on a specific model to get to a simpler model. The simpler model is called the restricted model because I'm imposing a restriction. I'm saying I have information on comfort, but I'm not using it. I'm saying beta c is equal to 0. That's a restriction I'm imposing in model. So when I want to compare these, so this becomes your LL of R, and this becomes LL of UR, the unrestricted model UR, the restricted model R. Okay, so now the likelihood ratio test is combined as 2 times LUR minus LR. Okay, and then you compare this difference to a corresponding chi-square parameter, where just like in statistics, there's a table depending on number of restrictions. For example, here our model 2 and model 1, the number of restrictions is only 1. Okay, it's based on the number of parameters. Here we have 3 parameters, here we have 4 parameters. So the difference is. So we will look for square value for 1 degree of freedom. Okay, if you look for a chi-square table, you can see that the chi-square value change at 90% or 90% changes based on degrees of freedom. So if this test statistic, let's say it comes out to be 5, and the chi-square value is 2.5, 5 is greater than 2.8, so that means the unrestricted model is better. Okay, now if you only get, let's say, 1.5, that means it is less than that. So what that tells you is, I mean, the restricted model equal to the unrestricted model. So we don't need a more complex model. We can actually go with the simpler model. So whenever we want to add complexity, we need to show that that is actually helping. So that's why this test statistic has to be significantly large. When it is large, it tells you that yes, if you use an unrestricted model, you are actually providing extra information to the data, to our model, so that's helpful. If it is not helpful, why do we need a more complex model? And we want to keep adding parameters in the model for the sake of complex. Okay. So always, whenever we develop a complex model, you need to check this. You always need to ensure that the complexity is actually improving what we are trying to do. So, yeah. So it comes from theory where they have tested that with the test solution. The two comes from that. So basically, the model offers additional improvement only when 2 times that, because there's a derivation for that. We won't go into no, there's a statistical. So basically, what they do is they look at equations when the limit of the data set moves to a large data set. So, and then they derive. No, that's not what is come from sample sets. So what I'm talking about, it's not geometric method. What is happening is when you have 20 data points, 100 data points, 1000 data points, million data points, infinite number of data points. So if you have infinite number of data points, you will get the population. Right? So that's where they derive this. So given that, you have this property that works out. So again, this is helpful when the two regimes or the two systems that you are comparing are nested with these. But if they are not, you can use AIC and BIC. Okay, AIC includes criterion, BIC includes criterion. Again, they also provide penalties for extra parameters. BIC imposes a stricter penalty than AIC. So BIC is a more preferred metric. If the model performs better based on BIC, that clearly gives you evidence that a more complex model is offering better performance than the simpler. So now the next aspect we want to talk about quickly is marginal effects. So if you have a utility structure like what we have here, this gives you information. Right? If beta is negative, it gives you information that if travel time increases, so the more probability for the alternative will go down. But it does not tell you by how much. In linear regression, it's different. In linear regression, because we have an equation that says y equal to 0.5 plus 2 times household size. Okay. So in this, elasticity or marginal effects are very clear. If household size increases by 1, what happens to y? It increases by 2. Your beta directly tells you the marginal effect. Okay, so I don't need anything complex for linear regression. So in linear regression, the coefficient itself gives you a sense of what is the impact of the variable. But that's not the case here. Okay, if let's say my beta tt is minus 0.05. Okay, so what does it do? If travel time increases by 1, my utility reduces by 0.05. But that has no direct bearing on what happens to the probability. So for that, I need to compute the probability, which is again, if I want to compute the probability, I'll have to do exponential of Vd over exponential of Vd plus exponential of Vd. So it's hard to tell what happens when Vd reduces by 0.05. Okay, so for that reason, we look at what are called marginal effects. So what that does is it looks at what happens if I change my x a little bit to probability. I want to compute for a small change in x, what is the change in the probability. Okay, so it is a little bit nonlinear. So change in probability due to change in independent variable. Okay, so what that means is looking at dpd over dx. Okay, x changes. So again, x scale for any of all of you can look for anything in this, right? So we are looking at how probability of drive changes because of change in travel time. Okay. Now, what happens is there are two travel times. Right? So travel time drive will change probability for drive, but changing travel time for transit also will change travel time probability for drive. Okay. So that's why there are two elements. We call them self marginal effects and cross marginal effects. So if I'm looking at drive by changing drive travel time, then that would be self marginal effect. If I am looking at drive by changing transit travel time, that would be cross marginal. Okay. And vice versa. Right? So we can have something for transit also. By change transit, then it will be self marginal effect for transit. By change drive, it will be cross marginal for. That clear? Okay. So we can again it will be a formula to do this because I am taking the derivative now not with beta with respect to x. Okay. So I have to take the derivative of this function, which is the probability function, with respect to x. So to think of this as the bd has beta naught plus beta tt into x tt plus something and so on. So I'm only focusing on this one, let's say. So I'm going to take the derivative of this. So you will get beta. So first of all, you have this nonlinear term. So you have to take the derivative of that, and when you go inside, you take the derivative. I'll show you quickly. So this is the expression. So I'm going to write this just to make it easier as q. Okay, the denominator is q So now I'll take the derivative of the QB. So Q times, so when I take the derivative, Q times derivative of the top one. So e power beta x is e power beta x times, I have to take the beta x only. When I take the derivative of beta x, all other x's I don't care. I'm only changing one x out of the set of elements. So there will only be beta here that comes. Okay. So I'm doing it as a cross elastic. Kth variable for transit is altered. Okay. So then you So then once you have this, minus you'll have this times derivative of q. Okay. So that will come because transit is changing, nothing will happen to x's in that. Okay. So you can simplify this. It is because of the logic formula, it simplifies pretty well, and you actually get a nice formula. You'll get beta times dn and dn. So it is a function of beta. Makes sense that beta. Marginal effect has to be a function of the coefficient. The coefficient is large, you want a marginal effect. The coefficient is small, you will have a smaller marginal effect. But it also depends on the current status. So what is the current share of transit and drive for that person? So if your share is equal, the switch elasticity will be higher, right? Because 0.5, the highest value you can get for a product which adds up to 1 will be at 0.5 times 0.5. Okay, everywhere else it will be less. So what this tells you is if the two modes are competing very closely, so the mode shares are around 0.4 and 0.5 for each alternative, beta has the largest. If you have transit is being used only 0.1%, 0.1, and this is 0.9, this reduces a lot. Even if the beta is large, 0.1 times 0.9 is 0.09, it makes it small. But if it is 0.5 and 0.5, you will have 0.25 times beta. So what that means is elasticity and marginal effects are important or play a heavier, stronger role when there is strong competition. So think about how you search, right? Again, maybe that's changing now, but Google has such a significant advantage. With other search engines are making some change, but there's no elasticity with it because people are so used to using Google, they're not doing their marginal effect of improving something a little bit does not show. But now with probably ChatGPT and its own search, there could be change that could happen. So when there are two alternative, so this is something that we see in transit a lot. Right? So the first thing folks talk about is we are putting so much money into transit in many regions, but nobody is using it. Again, the changes you make in transit times don't show effect because of this problem. Because especially in the leadership, you have 90% of the people are using drive mode. So any improvements you make in transit are watered down because of how the mode shares move. Okay? The nonlinear relationship kind of reduces the impact of elasticity. So you need to be prepared. You need to tell policymakers when they're talking about investing money, little bits of money is not going to change the whole picture in the urban region. It is going to appear like it's not helpful. It is the situation of how the mode split works when you have a very huge. Okay? But hey, when in cities like Montreal where the car share is around 40%, public transit and metro is around 30-40%. In those cities, any improvement in transit shows very good difference because there the modes are actually really competing with each other. So improvements matter. Improvements work better. So in those, so it's self-fulfilling story. Basically, in cities where transit systems are good, any improvements show rapid changes. In cities where transit systems are not currently used well, improvements don't make a difference. So it becomes that cycle of good and cycle of bad in different context, and you have cities in Europe where transit feeds on itself. Any improvements they make, more people tend to use transit because it's convenient. It's useful. In the US, we tend to be on the opposite side. So this is important to recognize when you are suggesting policies in your urban region, whichever region you're looking at, the current share of modes matters. Okay, so that is what governs how quickly or how slowly things will change in terms of ridership, in terms of adoption. And so all of that comes from this relationship. Again, the cross elasticity will just be minus of Z. So again, marginal effects are good, but the small problem is what is that small change, right? How much text am I changing, and what is the percentage? What is the change? So more informative approach would be to figure out what is the percentage change in the probability of the alternative for a percentage change in. So if travel time is 12 minutes, a small change means I'm changing it from 12.01 12.006. It's a continuous relationship in the limit and we will calculate it. So we use what's called elasticity effects. So all it does is I am also looking at relative change. So instead of focusing on small change in X, how does probability change? I'm changing what is the percentage change in the probability per percentage. Then this is more intuitive, right? So if I change my travel time by 5%, what is the percentage change in probability for a trip? So again, even 5% improvement in transit, it's hard. It's not easy to do that. But you can actually see the by normalizing this, we can actually see how we can. So this is good because so if you write it this way, I'm just rearranging the terms here. So this is your marginal effects. I'm just multiplying marginal effects with x over b. Okay. So the formula actually simplifies. So I'm using the marginal effect formula to previous slide, and I'm just multiplying it like this. So you have the PTN will cancel off, and it will simply be beta, p, and x. So this will give you the percentage change in probability for a particular alternative relative to a percentage change in x. So the elasticity effects are I think are more useful in interpreting because it also captures the impact of x, the travel time, travel cost. This could be another way of capturing it. So again, just like marginal effects, we have cost and self elasticity effects also. Same formula that follows from the. It's not necessarily that multiple alternatives won't be the same. Because we have three alternatives. For two alternatives, it might be, but for three alternatives, it will be spread around. Yes. There will be changes in proportions. We use those reasons also, or the continuous value you have as time and so on. They just add up to the yes, those will are. So the ones where you have information of both, you can include that in both the equations as a generic coefficient. So it's a direct and coefficient for both. You can do that. But the attitude responses that you get each, you can read each more separately. Yes. So because they are you need to be careful in how you add them in the equation. So you not calculate them as pure potentials, and then you use that by more. two modes. There is private and yeah, they can enter in each equation appropriately. Yes. So the driveway response to drive questions can enter in the driving equation. The public transit questions can enter in the public transit equation. That which means the other is zero for them. Yeah. So these are all elasticity effects that we talked about here are measured at the personal level. Now, if you want to look at elasticity at the entire data set level, what you do is you compute it for every person and then add it. That gives you the net elasticity. For one person, for another person it could be 5, for another person it could be 0. So to get the idea of elasticity across the entire data set, you have to take the average of elasticity of all the people in the data set. So now we will talk about specification. So this is how you will specify your model. Then you have two alternates, right? So you have U is your total unity, V is the observed, epsilon is the error, and we are trying to understand what we can add into these. So here I have car and transit, I have travel time, travel cost, number of transfers. Okay. So here I'm using beta 1 for travel time, beta 2 for travel cost. Okay. So in some cases, people use different coefficient for travel time and travel cost. I don't usually do that because people's sensitivity to travel time has to be so. If you are looking at making changes to a transit system, making changes, adding new modes or new services, if you don't use a common coefficient, you are creating an issue for model because if you use a separate coefficient for car and a separate coefficient for transit, you are implicitly saying travel time is perceived differently in different modes. Okay, that might be the case, but still, what if you have that? You cannot get a good mechanism for the interaction between the different modes. So if you one argument can be travel time in public transit is very different. Because I don't get to listen to the music I want to listen. I have to share my space. So there are people that say that that's why we should have different coefficient for travel time in car versus travel time in public transit, because public transit can be more burdensome. But that is not the issue of travel time. That's an issue of the mode itself. So the constant should take care of that, or you should have variables such as comfort or other variables which are different from travel time. Okay, so the reason we like to use the same coefficient is now if I use the same coefficient, if I make improvements in travel time, I can assess the impact of those easily. Also, if I have a new mode that is introduced, for example, right now metro is not available in Circle. In the future, they're adding metro. So if you have a separate coefficient for car, separate coefficient for transit, how do you know what is the coefficient for metro? So here, by keeping it generic, what we are doing is we are saying people's sensitivity to travel time does not change based on mode. They are sensitive to travel time the same way across all modes. So any new mode we add can be compared using that logic. Okay. Same thing with the travel cost. Okay, so we impose the condition that all of them are same. So that way, if you have 4 alternatives, 8 alternatives, or 2 alternatives, the number of coefficient for travel time and travel cost are just 1. You have 1 coefficient for travel time, 1 coefficient for travel time. You can only capture the difference, right? So one of them has to be 0. So if I have a constant here, then you cannot identify. So in your model, remember, you can only identify the difference. You can only capture dq plus dq. We don't know the absolute values. So for simplicity, I make one to make my life easy. Because all I can do is the difference. If you put a in cancel. anything other than 0 here, you can't identify. What I mean is you cannot estimate the mod. It will be undifferent. See, the probability is a function of difference. So, difference between drive and public transit is 2 units. Now, how many ways can you get the difference? You get in infinite ways. 3 minus 1, 4 minus 2. So, I make one of them 0. I am not making these 0 because these two change. Travel time here and travel time here are different. You can think of this as I am actually capturing the difference of travel time. It's easier to see if you keep them separate. That's why I keep them separate. This is the same as making PQ to 0. The whole thing 0 and beta naught plus beta 1 times PBC minus PBB. Difference of travel times, difference of travel cost, and effect of number of transfers. So we are theoretically making one of them completely 0. We cannot because utility of 2, 4 has no meaning versus 1, 3. So we have to make one of them 0 and find the other. No, it is a mathematical need, not an assumption. Because the probability is a function of difference, not direct utility. So again, utility is a latent constant. There's no utility. There's nothing called utility that people are really doing this. So we said, okay, let's do this. Now when we're doing that, the probability is a function of difference. Okay. Now all I can estimate is the difference. So if there are two items and all I know is their difference, there are infinite possibilities for the difference. So to be able to identify one unique value, fix one of them to 0. Okay, if I don't fix it, my code will keep running forever. It will try to find a possible value for 2. Let's say, and it will keep running 3 minus 1, 4 minus 2, 5 minus 3. There is nothing to stop. That's why we need to fix one of them. There will be an infinite solution. So here, for utility, again, the interpretations are relatively simple. So what does beta naught represent here? How would you interpret beta? What does it represent? Okay. Generic preferences, right? Okay. More. You explain what the constant captures, but what does it mean physically in the utility perspective? Yeah, beta naught is the difference and everything else is constant, right? So if beta naught is positive, what that tells you is if everything else is the same, people have a preference for the car. Okay. So beta naught represents the intrinsic preference for car versus public transit. Positive or negative. If it is negative, people in the region prefer transit. If it is positive, people in the region prefer. Again, once you start adding variables, the interpretation of constant goes away. You can interpret it when you have only travel time and travel cost. But in general, after you add land use variables and other variables, you should not try to interpret the constant. It is what it is. You don't make it 0. You don't remove it. You retain it, and its interpretation is not very important. When you don't have anything else in the equation, so nothing else is available and you know, it will tell you what is the preferred alternative in that strategy changes. It's all betas. These are betas, all betas. Yeah, not beta 1, beta 2. I'm explaining this. So if you see beta naught greater than 0, everything else is the same, charge will be less than 0, charge is equal, both are equal. And one more thing we can do is because we have the equation where travel time and travel cost are interacting, we can start thinking about okay, what is the value of time. What I mean by that is, if I save 1 minute, how many dollars or how many rupees are people willing to pay me for that? So how can I? So if I save travel time, my I compensate for that by increasing the cost. So the net change in utility is the same. So a person who takes 10 minutes and pays 20 rupees might be might not change their choice or might not change the probability of the choice if I reduce travel time from 10 minutes to 8, so reducing it by 2 minutes, but increase the cost from 20 to 24 minutes. Okay, depending on your features, you can find that trade. You can actually find what is the money I am willing to pay to compensate for an improvement in travel time by 1. That is what you can do from the relationship. So if you look at the equation, so because B is a simple way to figure that out. So B is a dimensionless unit, scalar unit, right? So both utilities are there. So, but the unit, 6 minutes. So effectively, beta 1 will be 1 over minute. The unit for beta 1 will be 1 over minute because the product of these two should be a scalar. So this is 1 over minutes. This is 1 over dollar per minutes. So beta 1 will be 1 over. So if I do beta 1 over beta 2, be 1 over by 1 over dollar. So that ratio will give you the relationship or the value of time. Right? So how many dollars I'm willing to pay for 1 minute of change. Or if you want to convert 1 hour, you can do that. So basically, all I need to find the money value of time is take the ratio of 2 coefficients. You can apply the same idea for any two interactions. Right? If you want to look at how much money people are willing to pay to avoid a trust, take the same ratio. You can do the same approach to figure that. What I'm showing here. Value of time, money value of time is beta 1 over beta 2. You can also come up with time value of transfer. How many minutes is equal to 1 transfer? So in public transit, this is a very important metric because you can look for people who want to go on a direct route versus I have to transfer at a particular location. So in addition to the travel time, people usually place extra value on transport because I have to get down from the bus. Whatever I'm doing, I have to stop that and go to the next bus. So I have to focus on finding the next bus and going. So there is a value people place when they want to avoid transfers. So I think I have an example here. So you could take a local bus and then an express bus that gets you to your destination, or you can take the local bus directly. Okay, so the travel time on ACB is only 35 minutes. Local bus is 45 minutes. So again, if you think of it purely based on travel time, everybody will be taking ACB. But depending on what cost people impose to themselves based on the transfer, the choice can change, right? If the time value of the transfer comes out to be 12 in your model, so that means the travel time from ACB is not 35, it's actually 35 plus 12. Okay, so this is helpful for transit agencies in planning their routes. So they'll say, okay, if I build a new express route, how many people will switch their current travel patterns? Okay, so again, if we don't know beta 3 is only 8, then this person will probably take 8. So that's how you can understand what is the impact of the transfer or new routes that you're building. So I think I have some examples like that. beta 1 over beta 3 is 10. In that case, both are equally likely for that person. So they can choose A. Okay. So you can do this with, once you have a specification, you can do it with any coefficient, right? So you can do beta 1 over beta 3, beta 1 over beta 4, if there's something like that, you can come up with. And also you can get money value of transfer, that would be beta 3 over beta 2. Okay, so how many dollars people are willing to pay, or how many rupees are willing to pay to avoid a transfer. So until now we've talked about adding what are called alternative factors. So travel time, travel cost are specific to the alternative. So there's a travel time for transit, there's a travel time for car. Right? But what about adding the variables such as gender and income? These are individual level variables. These variables do not change. So the way to add them is, again, just like the constant, they can be added only in one of the two equations. You cannot add them in both. The male variable and income variable here. So what does beta 2 here? So right, so it captures the difference in utility per car between men and women. Right? So if beta 2 is positive, it means men prefer to use the car more than women. Okay. So utility per car increases for men compared to. So what do you think beta 2 is positive or negative? I think in the Indian context, it's potentially positive, but in the Western context, it's usually negative. Uh, Not because men are want their wives to drive or partners to drive, because women are taking their kids to school most of the time, so they get the car. If you're using transit, you take the transit. Men take the transit for that. So, in terms of income, usually beta 3 is positive. The more income you have, the higher the income, the higher chance of using that. Okay. Explaining this here. So, we talked about money value of time. We said so BOTT is beta 1 over beta 2, but there is an implicit issue. So, we are assuming that money value of time remains same for everyone, right? So, when we do a beta 1 over beta 2, it's purely a function of travel time and travel cost. It is not sensitive to the right? Money value of time for a low income individual versus a high income individual should be different. We are not capturing the effect of income. So there's a way we can do that. What we can do is, instead of focusing on total cost, we can identify how the cost relates to income. Okay? So 200 rupees per person making 12,000 a month is different than per person who is making 1 lakh per month, right? So we can capture that by representing, instead of using TC here, I can actually use TC over income. Okay, if I use that, now if I have income in my, say beta 2 over income, beta 1 by beta 2, income will come into the picture in the commission. Let me show you that. So I'm using this variable for cost, instead of using just TC. Now if I do that, my coefficient will be, the ratio of beta 1 to beta 2 will actually be beta 1 beta 2 by income. My money value of time will become beta 2 times income. So as income increases, the money value of time increases for that person. Does that make sense? So this way, we can actually get allowing for different money values of time for different people in the. So this is more realistic. And so other ways of doing this would be segment the population. You can take three data and say more choice, income, but this gives you a more natural way of doing it and gives you easier income. If they are giving, so this is assuming there is a continuous value available. If it's not available, you can capture interactions per beta 2. So what you can do is you can do beta 2 for travel cost, general one. Then you do beta 3 for travel cost for flow income and beta 2. So for doing it as beta 1 over beta 2, you do beta 1 over beta 2 plus beta 3. Yeah. Okay. No. You should use categorical dummies and try. Because see, what we are saying is when we use income the way I showed here, you are saying the money value of time keeps changing. Right? As income increases, it keeps changing. That's not necessary. I mean, even if you can at least do a stepwise approach for 3 income levels. So like if you're computing, let's say less than 50K per annum, 50K to 1 lakh, 1 to 2, and then maybe greater than. So let's say we have these 4 categories. If you can get money value of time like this, this is also useful. Yeah. So okay, we are trying to do the best because income is a variable that's very hard to ask. Right? People don't want to give out their exact income for different reasons, especially because of income tax consideration. They are like you. Yeah, it's a household survey. Possible. Okay, it is possible that there will be more forthcoming with that. The thing is, can you travel cost over expense? Okay. Yeah, that is possible. The only thing is depending. I'm thinking about this any particular income here because yeah, expenditures. If the expenditures by more are reasonably similar, it's okay. But I mean, because if you have a expensive car, or the expenditures will be higher. Expenditures by transit and the car. But the thing is, you might be two groups where if you are a transit person, your expenditures on the lower side. If you are a car person, your expenditures are substantially higher on an annual basis. Yes, the computing cost is complex for that reason. Yes, you should theoretically consider all components, or you will have to talk about. I'm only talking about operational costs. Yeah, you do that, but expenditures, I think the way he is collected as the demand variable. So you ask the individuals what is their expenditure. So I'm only worried about there will be too much difference in expenditure. So that kind of provides information to the model that this expenditure should be car, this expenditure should be done. That's the only thing. Because if they are specific to mode, you're violating the independence. Expenditures are only high for one group compared to the other. That indicator itself will bring you to that. So it will become a very big exponent. The add segment power in that sense. So as long as the means and the standard distributions are not very different. So if you plot these distributions, then if you can see two clusters where the first cluster is transit sector, you cannot use it. Because that is it's something that happens. You're using that as the inventory. That's the thing. The income at the end of the day is income. It's powered by how much I spend. So it's okay. But if my node decides how much I spend, how can I use that as my independent? Because it's something that happens after the choice. So that's something you're thinking. But if it is not like that, it's so binary models for binary models are also we have more alternatives. Additionally, you have travel time, but you can consider you know that travel time is not monolithic. There is out of vehicle travel time and in vehicle travel. For example, if I am going to take a trip for an hour, right? If I wait for the bus for 15 minutes, it doesn't feel that bad. I'm waiting for the bus for 15 minutes. Now, if my bus trip is only going to take 5 minutes, if I wait for 15 minutes, it doesn't feel fun, right? Because so there is when they are waiting, when you are driving in your car, you listening to music, whatever, but you have to come 12 minutes after you park. Again, that 12 minutes feels very burdensome. You think about that differently than the 30 minutes of driving. What you might have in your from the when they are waiting, travel time to multiple normal, between in-vehicle travel and automobile travel. And which you think is vehicle travel time more burden. So you'll get a coefficient. So beta 1 beta 2 beta 3 than the beta 2 of more negative. Okay, we can check that. And so that's something that is travel time to multiple normal. So it is in-vehicle travel and automobile travel. And which you think now with transit, even further wheel travel and more classified, so you can actually say a coefficient. So beta 1 beta 2 so beta 2 gives you more negative. You have to check that. So that's something that you have to make. You might further in data is available, or you are able to get some geocoded information that you can draw the distance to the bus stop, then you can actually start it. But this is a good system to look at. Yeah. So the only thing is that there's a range of waiting time will happen. Right? We don't have because on that particular day we don't know what exactly happened. So you could say use frequency as an variable. Yeah, because what you're doing is effectively half of the frequency, half of the and is what you're using as waiting time. Okay. So you say you use the frequency variables. Yeah, or you can simulate particular multiple times, not once. So yeah, that you can use. That you can use. If they have waiting time that they will face usually with the user. Just like we had the effect of income moderating the effect of cost, we can do something like this. So you can also try using OBDT as OBDT over distance. So what that means is if I'm going only 2 minutes, 2 miles versus going 20 miles, my burden for OBDT is as bad with 5 minutes versus when I have a very short. Okay. So sometimes we can also use in the specification and beta OBDT over distance. Okay, so that kind of reduces the effect of OBDT when you're going long distance. So far, again, everything we learned about the specification directly translates to multiple alternatives also. We talked about 2 alternatives, but it directly translates to multiple alternatives. So now, in the previous case we talked about, we had 2 alternatives. So now if we have more than 2 alternatives, how do we develop the model? Gives rise to what's called a multinomial logic model. So when we I between 2 alternatives, we said I should be greater than or equal to u. But now when you have multiple alternatives, you have a lot more alternatives than 1. What we need is probability of ui is greater than equal to uk for all k. This is the condition. When we have more than 1 alternative, or sorry, 2 alternatives, what we are saying is I choose the alternative that gives me the highest value, right? So not only should u1 be greater than u2, u3, u4. If I need to choose 1 as alternative, let's say if I'm interested in alternative 2, p2 should be greater than p1, be greater than p3, greater than equal to p3. Simultaneous. It has to hold simultaneous. All of it. Right? So it has to be greater than j minus 1, k minus 1 alternatives simultaneous. Okay. That creates an issue because when you have only 1 pair, you are looking at a distribution between I and j. But now this, you are looking at simultaneously matching k minus 1 pairs. So there are k random variables, right? Because each of these will have epsilon 1, epsilon 2, epsilon k, and so on. So we are trying to look at ensuring k minus 1 distributions are simultaneously managed. Okay, so that's what creates the complexity. For a long time, people did not use multinomial logic model because they did not figure out how to handle these k minus 1 dimensions. So this would be the so in a binary logic, we just said this has to be managed. You have to have epsilon less than vi minus vj. But in a multinomial logic model, you potentially have 20 alternatives. So there will be 90 variables in this equation. So that would give rise to, here it's a univariate distribution, that will give rise to a multivariate distribution. Because simultaneously, epsilon 1, epsilon 2 minus epsilon 1 should be less than this. Epsilon 3 minus epsilon 1 should be less than something else. Epsilon 4 minus epsilon 1 should be less than something else. So all of these have to simultaneously happen, which is nothing but multivariate distribution. Right? If you have a two-dimensional distribution, epsilon 1 should be less than something, epsilon 2 is less than something, then you have a CDF function for that. So multivariate CDFs are much harder to handle. So that's what I'm doing here. So PIN this in this fashion. So here, I'm not showing the derivation here, but if you use this approach, it will become a multivariate distribution going from minus infinity to this for this distribution, and then there's still epsilon system. I integrate that also. Okay, so that's what gives the overall. This is the overall function that has to be integrated. Okay. Again, first person who did this integral got the Nobel Prize in 2001. Daniel McFadden was able to do the integration for this equation, and that's when, until then, every choice was modeled as a binary choice. You have multiple alternatives. People said, okay, if I'm interested in the third alternative, I'll do 3 versus everything else. If I'm interested in the seventh alternative, I did 7 versus 3. This derivation was managed. People could start actually handling multiple alternatives. We're making several assumptions to get to this. A very nice formula that looks like this. It's exactly the same formula as the binary logic. Only thing happens is the denominator will have 4 terms. So 1 pi over all. So the formula, I mean, once you derive it, you think, oh yeah, that's obvious. That's how it should be. But you have to prove that it happens that way. And but when you say makes all this. No, it's not. Because the utilities denominator will change. If you only do 1 and 2 and get the probability, you are not looking at all 5 of them. How will you know that a priori? When you are estimating, see, you know your beta, yes, you know that. But to get your beta, you need probabilities. You have to maximize the logarithmic function. So once you estimate your model, yes, you can play around with a lot of things. But to get to that, you need the probability expression and the probability function. So one thing I talk about is when we are to get this derivation, we make some assumptions. Okay. So the first assumption, again, all of you might heard some of these. The errors are independent. We assume that errors across people, errors across alternatives are independent. So again, that's not necessarily true all the time. There are people who like they will not take public transit. So those two are independent. There is a correlation. And we also make the assumption, so talking about this here, where our epsilon will affect our choice, and we are assuming that epsilon is independent. Okay, so this is one of the implicit assumptions that usually is binary. Okay, then we are also assuming that the variances of all epsilons follow the same distribution. So what that means is, if my error car looks like this, my error for transit should also look exactly like this for all alternatives, all people. Right? That is not possible. I mean, for some people, either they like the car, so if I like the car mode, maybe I'm like this. Okay? For some people, they like transit, so they might have a system like this. So what that means is, it is not possible to imagine that all of them have identical error distribution. So this is what gives rise to what's called IID error. So we assume that errors in the multinomial logic model across alternatives are independent and come from identical distribution. Okay, but it's not necessary. So independent and identically distributed for all. Okay? So if you have different alternatives, it's not necessary that if you look at this set of alternatives, right? So person has carpool, bus, train, metro, walking. I mean, how can car and carpool not be common? Right? There will be a lot of factors. It's like sitting in a car, so either going alone or going with another person. So these two alternatives are likely to have a lot in common compared to bus, train, and metro. If you have a preference for one of these modes, you have a preference for all three of them. Right? Because you are okay with public transit, or you have a positive feeling with public transit, then all three public transit modes are similar. So it's unlikely that this and this will have a different error. Okay, so there is commonality. Similarly, if you prefer walking and biking, there is some there will exist some dependency that exists between the order. So it is still they, they, they are still shared nodes, right? Relatives and metro are very different. But compared to car, will you say are they close? So what we are assuming in our model is all are equally independent. That is what still. So even forget about the similarity. If percent are very different, they are not independent. Right? Because if people who like metro don't like bus, that's a relationship. That's all. What we are making an assumption is all of them are independent. My preference for bus has nothing to do with my preference for metro. But that is why. So it could, the violations can come in many. So we could have an interaction between the two in the observed part, saying people who prefer metro will have a negative correlation. So that should be the correction that we do in that case. So we have to be careful in how these assumptions come into the picture. So there are many strengths when you look at part because of the simple and beautiful formula that we have. It's very easy to estimate. So we can run the model easily, we can interpret that easily because we have coefficients for each alternative. You can talk about that. And because of the functional form of the objective function, you are guaranteed a global solution. Okay, when you run any approach to estimate the model, it will make sure that you have an optimal solution which is globally off. Okay, so that's also helpful. But of course, it doesn't come. So some of the things that the logic model does not do, it allows for variation, taste variation. What that means is, if I use an answer that, for example, if I use income, I can tell how things change based on income. But it cannot incorporate taste variation based on unobserved factors. So, for example, environmental friendliness. Some people might, two observationally identical people might have different environmental preferences. There are some people who don't really care about the environment, then there are other people who are extra care. Right? So there are differences in behavior like that. So those are harder to capture in a multinomial notion. And another important problem is what is called the IIA property, independence from irrelevant alternatives. So let me write that. So if you have two alternatives, so let's say we have 5 alternatives, the probability first alternative would be E over B1, E over B1. The third probability will be E over B3, same denominator. Okay, so now if I take the ratio of P1 to P3, the denominators will cancel. It will be E over B1 or E over. So, what is the how the two alternatives interact simply depends on the two alternatives. Right? No other thing matters. If the ratio of P1 to P3 changes, that change is purely a function of changes in P1 and P2. So, alternative 2, alternative 4, and alternative 5 are. So, in a multinomial logic model, we implicitly assume irrelevance of other alternatives. By focusing on these two, I don't really care about. But is that possible? I mean, if you are choosing from 5 alternatives, how can relationship between two alternatives be independent of everything else? Right? Mathematically, that's what happens in this model, but that is an issue. So it can create unexpected outcomes. So, for example, I don't know how many of you have heard about the blue bus, red bus example. So let's say there is a city where currently a red bus transit service runs, and then so now what the city did is they introduced transit bus. It's identical, no change in route, nothing. It's doing that. Okay. So what should happen? What should be the mode shape? So now before the blue bus was introduced, this was the mode shape. Okay. Now that blue bus is introduced, what do you expect it to be from your interpretation, from your intuition? Yes. It's an intuition, not what should happen to the time. It should not change. Right? All you did is you change the color of the bus, half of the buses you changed, and you're calling it. Right? So it should be 0.5. It should be right because nothing has changed in the people. All you are doing is you pay. But because we have alternative, these two should have the equal. Right? But now, if you compare these two, what happens to these? So here we have B1, B2. Here now B1, B2, B3. So based on the what should be the ratio of utilities per 20% groups? 1. Right? It should be equal. So we have equal to B. So groups is also equal to B. So now what will be the shades make them ML? It will be point. So we actually have just by coloring the bus from blue to red and calling it a new mode, and then let's increase the share for that from 0.5 to 0.6. That's if you can really do this in the world. Right? So this is the manifestation of the problem of independence of the period. Again, this is a very absurd example. Okay? In reality, IA is not this bad. It doesn't create such an issue. But this is just to show you at an extreme, it can be very bad. If you run into a scenario, because we don't know, right? You wouldn't know when you develop your model and run your analysis, you wouldn't know how much role IA is playing unless you test for it. There are mechanisms to test for it out. So this is an extreme example, but the independence of irrelevant alternate can potentially create a huge error in your model. Okay, so it's a good practice to see if you can check for whether the IIA exists on data set by running more complicated models, but it's something to be available. Okay, so there are 50 buses in the city, 25 already before now. Left, right? 25. So there's no change, but it's a new mode. We're calling it a new mode. So if you estimate the mode share based on utilities, the probability for bus will be 33, new bus will be 33. So if we avoid these scenarios, we need to make sure and run prime. But again, because it's not always bad, it also is helpful in some scenarios. Because if you think about location choice models, where you are looking at destination. So you are looking at an origin for a trip. So you are in Warangal, you want to watch a movie. So there are many destinations you can go to. So potentially, entire city of Warangal is an option. So if you have traffic analysis zones, usually you can have 1,000 zones or 500 zones in an urban region. As we want to do more detailed models, the number of zones that we want to use, traffic analysis zones, are increasing. For example, in Dallas, we use the 5,000 zone system. There are current cities with 8,000 zones. So, theoretically, we are developing a model for that. Every other zone is alternate. So, the number of alternatives can go to as high as 8,000 or 5,000 or in the orders of thousands. So, in that case, compiling data for 1,000 and modeling that is very computationally intensive. It takes a lot of time. Especially if you have 2,000 records, if you are doing 2,000 destination for 2,000 people, if you are modeling destination twice, your data set will have 2 million records. Because you have 2,000 and for each of them there are 1,000 alternatives. Right? So it is computationally intensive. using IA because if you develop a multi-component model, I don't care about the alternatives. I can actually do a very good sampling approach. So there is proof to show that a model that you estimate with 30 alternatives randomly sampled will give similar results as a model which estimate with 1,000 alternatives. Okay. So that in that case, IIA helps, and you can use that to run the model more efficiently. You can run instead of using 2,000 times 1,000, you can use 2,000 times 30. Suddenly, your sample sizes are smaller. It's very easy to understand. Okay. So this is the second paper. So he got a Nobel Prize for first derivation, and he also proved that you can do sampling in alternatives to run larger models in location choice. And again, the marginal effects are very similar because the formula is very similar. Nothing changes. The only change in the previous one, we had 1 minus PIN because there were only two alternatives. We could say this was transient. Here we cannot say that because it could be all other alternatives, right? So we have to leave it as 1 minus PIN. That's the only change in marginal effects from binary to polynomial. The self-cross everything transfers the same way. Elasticity also transfers the same. One of them will get cancelled. The slides are there if you're interested in exact details. So interpretations get a little tricky when you have more than two alternatives because if you have income variable, in alternative 1 is the base, you are introducing it in alternative 2 and 3. Okay, so these are the coefficients. Let's say you get the coefficient as the base is effectively 0, 0.25 for the second coefficient, 0.55 for the third coefficient. Okay, the effect of income on second alternative is positive with a coefficient of 0.5. Third alternative is positive with a coefficient of 0.5. Okay. So, what happens if income increases? Based on those numbers. You have three alternatives, V1, V2, V3. V1, no change. Right? Income is not part of the equation. Here, it will change by 0.25. Let's say we increase by $1. This will increase. Okay. So now, what can we say about probability? Right? So P1 will be P power V1 by P1 plus P2 plus P2. Let me write. So when income changes, this has no impact. So the numerator has not increased. Okay? But what is happening in the denominator? P2 has increased. P3 has increased. So the denominator has increased. So what happens to the probability for the first one? It will go down. Okay? This is very clear. Okay? Because numerator increased, numerator no change, denominator increased, the probability has to go down. Let's come here. Numerator increased. L1. Right? Here denominator also increased, but the numerator increased more. So here the probability will increase. Because this is the highest magnitude. Now, this is not so straightforward. Right? Because this is in the middle. So there is a little bit of an increase here. There's some increase in the bottom. So what happens is the extremes are easy to pin down. You can tell the that V1 will always go down, V3 will always go up. But V2 or the alternative 2, we don't. We'll have to do it for every specific case. It depends on the rest of the variables, rest of the utility terms. Okay, you cannot a priori tell what will happen to alternative 2. Alternative 2 would go up or go down. What that means is if the difference, so V3 is increasing so much that it actually draws from V1 and V2. Or it is possible that V3 draws only a little bit, V2 also draws a little bit from. So there are many possibilities. So we can only tell about the lowest alternative and the highest alternative. This will always go up, this will always go down. This depends. Okay, if you have, this is only if you have 3 alternatives. If you have 6 or 7 alternatives, again, then also we can tell about the extremes, but in the middle we cannot tell. Okay, so that is how this will look. So this is a simple model. What I do is here I am showing you a mode choice model for different alternatives. Driver with passenger, walk, or bike, and transit. And I am giving you different coefficients. You see travel time coefficient is there, and there are so these are constants. One of them is 0. Then you have person and household characteristics, household activity decision. This is what is a commute mode choice. There are decisions about activity participation and absence. Okay, so as you would expect, if you have a vehicle, if personal vehicle availability is high, you are going to use driver. If you are employed, you are less likely to be a passenger and use walk or bike. Get this data set from Dallas Fort Worth. So these are expected relationship driver. So if you look at if your activity is work related, you are less likely to go as a passenger. If you are doing shopping, you are not likely to use transit or walk or bike. Again, these are expected relationship that you get from. So I'll pause here. I think take a break, and I will get back and start talking about another case study on mood choice.